90% of shipped goods move across the water in vessels like this, floating steel fortresses designed to withstand the physical power of the ocean. These ships are synchronized by a submerged counterpart, a vast network of deep-sea telecommunications cables that manage the high-frequency data required for international commerce. Public awareness of ocean acidification remains largely confined to the biological death of coral reefs and marine ecosystems. This narrow focus overlooks the industrial reality. That same changing chemistry is actively attacking the carbon steel hulls and telecommunications infrastructure that global trade is built upon. To understand the future of the global economy, we have to look past traditional market indicators and zoom in on the microscopic chemistry of seawater. This chart tracks shifting ocean pH. As water absorbs atmospheric carbon, acidity rises, altering the sea's chemistry. That acidity targets carbon steel, the primary material in the global fleet. Acidic molecules aggressively interact with the metal, stripping away atomic bonds that provide hull strength. This isn't a sudden catastrophic event. It is a continuous, invisible physical degradation that occurs at a mathematically predictable rate. Modern ship hulls are engineered with extreme precision. Immersing that engineering in billions of gallons of corrosive water means even fractional shifts in pH can drastically shorten the functional lifespan of a vessel. Marine chemistry has fundamentally shifted. It has become a proactive corrosive agent, relentlessly eroding our most expensive, critical industrial assets. When we move from microscopic chemistry to the physical fleet, the consequences of this erosion become immediate. Look at the severe weathering on this hull in dry dock. To prevent failure, vessels are pulled for maintenance more often than in past decades. To compensate for weakened steel, ships are frequently forced to reduce their oceanic transit speeds to avoid putting excessive mechanical stress on their compromised frames. This chemical process also threatens the deep-sea telecommunications cables resting on the ocean floor. Corrosive seawater accelerates the breakdown of the specialized protective outer housings and armored layers designed to keep these data lines dry. Once the outer shielding is breached, moisture infiltration leads to signal attenuation or forces emergency maintenance shutdowns, disrupting the high-frequency data flow used to coordinate port logistics. This microscopic rot in our ships and cables translates into the most dangerous element in global logistics: unpredictable friction. On a macroeconomic scale, these localized points of friction compound. A slow ship in the Atlantic and a data void in the Indian Ocean aggregate into massive logistical bottlenecks across every major shipping lane. As seen in this congested port, the result is a cascading effect of delays. When vessels crawl across the ocean or sit in dry dock, the entire global supply chain stalls. Current economic models are blind to this because they treat the ocean as just a distance to cross, not a deteriorating physical medium. Future trade policy requires a fusion of oceanography and macroeconomics to adapt to this fundamentally more hostile physical environment. Without bridging the gap between marine chemistry and trade logistics, the physical foundations of international commerce will continue to quietly dissolve.